divided by the limit as x approaches 0 of 4 times the limit as x approaches 0 of sine of 4x over 4x. Okay, so you won't have to write this step out right here. You won't have to write this out fully, but I just want to show you this today. Okay, that this is, again, using the properties of limits here. And what this simplifies down to is that this is just 7, because as x changes, 7 doesn't change. So that's 7. This is 1. Over here, down in the denominator, that's 4, and that's 1. So your answer is 7 over 4 as a limit. So that's sort of all I'm going to tell you about 7.1. It's just that this right here, really important. And you can use this to simplify certain expressions. Okay, so just to let you know what we're doing now, the question was, is there a limit for cos theta over theta? We're going to check it out. We're just going to do this quick little chart. We're going to do cos theta over theta and see what's happening here, see if there's any kind of value that's approachable, and we'll explore that. Okay, so when we quickly just fill out this cos chart here, as we're approaching 0, if we recall for the sine, okay, we're approaching 0 here. This is getting really, really close to 1. Like that's just inching up thousands and millions and billions of the place. But here, okay, so we're approaching 0 from the left side, right? What happens to cos theta divided by theta? We've got negative 1.7, and we've got negative 9.9, and we've got negative 999. So this is not approaching anything gradually at all. So there's just no limit that we can take advantage of there. It's just the sine. Okay? All right. So let's take a look at 7.2. And this is derivatives of sine and cos. Sine theta and cos theta. And I'm going to start off by drawing two graphs, okay, using the same sort of axis here, the x-axis, okay. So I'm going to draw, first of all, I'm going to draw the sine theta, okay. And I'm going to start from sort of a negative pi over 2. So that's going to be at -1, right? 1. So the sine graph looks like this. Okay, that's a positive pi over 2. Come down here, pi. And a negative 1 here at 3 pi over 2. And then up here at 2 pi. Okay? Alright. Not the best graph in the world. I get it, but it's going to be pretty close. Okay? You can follow along in your textbook. You can sort of see this on page 308. Okay. So what I'm going to do down here is I'm going to look at, and I'll do this in blue down here. This is going to be the derivative of sine theta. Okay, sine theta with a little prime there, or d over dx, or d over d theta of sine theta. Okay, the derivative of sine theta. All right. Now we know that derivatives are instantaneous rates of change. So let's graph some derivatives here, some tangent lines, and we'll look at their slope. So obviously here at pi over 2, we know that the derivative here is 0. So we're going to drop down here exactly. We're going to put a point at 0. Right? Okay, as we move towards 0 over here, right, our derivatives, okay, that's a negative, sorry, that's a positive derivative, right? And would it be, positive what? 1, 2, 3, 4? Well, if we think about it, a 45 degree sort of angle here would be 1, right? Let's say, and so if we move down here, what we find out is that once we hit sine of 0 here, we have a derivative that's going to be actually 1. Okay? So at y equals 1, at theta equals 0, we have a derivative of 1. All right, so all those derivatives, let's just get rid of some of them. Okay? There's the derivative equaling 1. So as we move along, it doesn't look like it right here, but we have a derivative of negative 1 right here. And then we have a derivative of 0 at 3 pi over 2. And then at 2 pi again, this is where the derivative is positive 1 again. All right? And if we take a look at all of these derivatives in the middle here, as they kind of race towards, okay, so then we get this sort of graph happening. And what does this graph look like? Yeah, it looks a lot like the cosine graph. And so what we learned from this by graphing the derivatives, rather roughly here, I apologize, but we see this. The derivative of sine, so d over dx of sine theta, equals the exact same graph as cos theta. Very important. And you'll see me write this sometimes, sine theta prime equals cos theta. Some people don't like that, but I don't mind saying that this is a derivative. But the derivative of sine is cos. Okay? Great. Okay? Let's do one real quick for cosine then. All right, let's do cosine. So this would be cos theta. And down here is going to be cos theta prime, or d over dx cos theta. All right? So if we graph that, 1 and negative 1, for cos theta, it's like this. And you guys are pretty bright, so you can tell right away that the cos graph is really the identical of the sine graph, just shifted, right? That's what you learned in pre-calc. So you know that a tangent line right here, okay, is going to be the exact same as it was for the sine graph up here, right? And so what value was that? Well, that was 1. So if this is y equals 1, we have a point there. The derivative here, 0. The derivative here, negative 1. So you're just kind of graphing these derivatives as points. That's a 0 slope, so that's a 0 on the derivative graph. Here's a positive 1 slope. So we're going up here to positive 1, and then we're back to 0. Okay? So, sorry, back to 0, and I wrote it there. Sorry, right here, 0. Now, if we connect these points, okay, remember, we're kind of focusing on just this part of the cos, right? Just one period from 0 on. Connect those points, and what do we get? We get something that looks a little bit like this. We fill in those values, and what does this look like? Now, you got to take my word for a little bit that they kind of behave like this, but they do. And what does that look like? Yeah, it looks like a sine graph that's been flipped. So that's a negative sign. A negative sign. Okay? So here we go. Yeah. Here we go that the derivative, d over dx, of cos theta is negative sine theta. And of course, this cos graph repeats itself, and so obviously, this is going to repeat itself as well. And there you go. You have another, another sine graph. So that's true all the time. So this is really important. The second derivative of this cos function. Okay? All right, so they are very closely related. Derivative of sine is positive cos. So sine, cos go together. Sine, cos, sine, cos. Derivative of cos is negative sine. So if you start with cos, you got to go negative sine. So positive, negative. Okay? Now, what is this going to help us do? Well, if we have y equals sine of 3x, okay? If this is now the graph, here's an example, okay? And I want to find y prime. I want to find the derivative of this graph. Now we know that this is the b value that we talked about in pre-calculus. So how does this change the sine graph? Like the sine of x graph, the plain old sine of x graph. Anybody remember? Okay. Does it change the amplitude, or does it change the period length, or does it move it left or right, or does it move it up or down? You were saying that you think it horizontal something. Yes, horizontal stretch. Now, what we have to, this is the b value. Now, what we have to remember is that the period length is 2 pi over b. And here b is 3. So the period length is actually 2 pi over 3 instead of 2 pi. So what that does is it compresses it horizontally. If b is greater than 1, it compresses it horizontally. All right, and now that's another lesson if you want to look back to that lesson, but or if you want to ask about that a little bit later, you can. That's not really important right now, okay? It's not really important, but I just thought I'd ask to see if you remember what this does. But when we're finding the derivative, what we want to envision this as, and remember, the sine by itself, okay, means nothing, right? It's not sine times 3x. That makes no sense at all. What this is it's one function, but it's a function within another function. So what does that sound like in calculus? We're taking the derivative. We have a function within another function. That sounds like chain rule. Yes, that's exactly what it is. And so what we have to do is we have to think chain rule. Okay? So we look at the outside function first, which is this sine of 3x. Can I take the derivative of sine function? I sure can. It is cos. And when we do the chain rule, we always leave the inside function alone first. But what do we do with the chain rule, though? What do we do with that middle function? Sorry? Yes, we take the derivative of the inside function and we multiply it. So the derivative now of this inside function, derivative of 3x is 3. And so our final answer is the derivative is 3 cos 3x. It's typical, and usually put the number in front there of the trig function. Okay, so if you got a times 3 in the back there, bring it up to the front. Okay, that's okay. Cool. Now, can you put the 3x in brackets? You can put the 3x in brackets. You don't need to, because they're like I say, this means the exact same as without the brackets. Okay. If this was cos of 3 times x, that would be the only thing that would be different. You would bring that x in front, so there wouldn't be a confusion. So yeah, you could put brackets there. That's totally fine, but you don't need to. Okay. So that means cos of 3x. Okay. All right. Let's do one more example here before we kind of get going a bit more here. So let's do something a little bit more challenging. Let's do, well, I'm not sure how you'll find this one, but, well, I guess I could do that. Function notation. I like this one. Cos of x squared minus 2 all squared. Okay? So, this notation, you have to try and figure out what the outside function is. The outside function is the cos. Right? Makes sense. Cos. The next function is this right here, including that squared. So we have the blah squared.